Today, on How It's Made. Electrical panels. You'll get a charge out of this story. Kites. These handmade models are flying off the shelves. Eyeglass frames. We have a look-see at the metal ones. And toothbrushes. A report that'll have you bristling with excitement. The technical name for it is a residential load center, but people usually call it an electrical panel or circuit breaker box. This enclosed metal panel is usually built into an interior wall. It contains the circuit breakers that distribute, protect, and control the home's lighting and power. This load center consists of up to 40 circuits. Each one has 1 or 2 breakers. Each breaker powers several outlets in the home. First, a powerful press pounds a sheet of steel into what's called a U-channel. At nearly a meter long, 35 centimeters wide, and 10 centimeters deep, it's part of what's called the tub, the load center's main casing. A worker then attaches steel components made earlier called tub ends. A spot welding machine fuses them to close off both ends of the tub. Workers feed an aluminum strip that's 100 meters long and 15 centimeters wide into a stamping press. The press cuts the strip into 50 centimeter long segments called bus bars. It bends each bus bar 10 times, creating 5 centimeter segments called stabs. The breakers will later snap onto these stabs. Next, a worker inserts each bus bar into a plastic component called a base pan. The base pan insulates the bus bar. This prevents us from getting electrocuted. Another press then inserts a plastic rivet, securing the bus bar to the base pan. The worker installs 2 components called neutral bars in the base pan. The neutral bars conduct electricity between the circuit and the wall socket. Next comes the main breaker. Its maximum capacity is 200 amps. Amps are the units of measurement for electrical current. If demand exceeds maximum capacity, it'll trip, meaning it'll turn off all power in the home. She makes sure it's sufficiently tight so that vibrations caused by street traffic won't loosen it. She also encloses labels to mark the breaker's pathways and an envelope with installation screws. Next, the worker puts the base pan assembly into the tub and secures the neutral bar with a copper bonding strap to ground it and prevent electrocution. She adds another component, one of 2 grounding bars. These ground each circuit. The breakers simply snap onto the stabs, making them easy to remove and replace if needed. Inside the breaker, several components interact to enable the flow of electricity. One is the load terminal, the entry point for the live current. A circular machine called Robot A assembles it and other breaker parts along its 16 workstations. Another breaker component is the bimetal assembly. It's an alloy of 2 metals and a magnet. It trips the breaker when there's an overload or short circuit. Next, Robot A welds a strip of silver, which is conductive, to what's called the contact arm. Robot A then positions the arm for welding with 5 centimeter long segments of braided copper wire. Copper because it's conductive as well as pliable. The robot fuses the copper wire to the contact arm and the bimetal assembly. The wire will flex with the arm to touch what's called the line terminal. This contact permits the electrical current to flow. Next, Robot A deposits the welded parts into the breaker casings called bases. This automated production line functions 24 hours a day, 5 days a week, and it produces a breaker every 3 seconds. Another machine, called Robot B, stamps the number of amps on each breaker handle. Then it connects a spring to link the contact arm to another part called the cradle. When there's an overload, the bimetal assembly causes the cradle to pivot and trip the breaker. Robot B deposits the spring and cradle into the base, then closes the base with a cover. This demonstration shows how moving the breaker handle triggers the mechanism that will enable the flow of electricity. If power demand exceeds the breaker's maximum capacity by 35%, the bimetal assembly trips the breaker and cuts the power. They cap off the load center with a metal cover called a trim. The warning label on it provides safety information and instructions. The load center is now ready for installation by a certified electrician. The earliest written record of a kite tells the story of a Chinese general in 206 BC who flew a kite over a wicked emperor's palace. He marked the line to measure the distance, then reeled it in. His small army then dug a tunnel into the palace courtyard, launching a surprise attack that conquered the emperor. Today's two-line kite, as the name implies, has two lines to pilot it. It can fly nearly 40 meters high. This kite is made mainly of a lightweight nylon fabric that is waterproof and fade-resistant. It's less than a millimeter thick, so it's reinforced with nylon mesh to reduce ripping. The kite's other components include nylon and elastic cords and straps, fittings made of leather, rubber, aluminum, and plastic, and carbon rods. The kite maker starts with a pattern made out of pressed wood. She marks out a piece of fabric and, with a few bricks to hold the fabric in place, cuts it diagonally. In sewing terms, that's called cutting on the bias. This will stretch the fabric and